Hi, everyone. Um, Welcome to another episode of the Common Lisp Study Group. I am your host, Ram Vadam, with Atlanta Functional Programming. Today, we are going to continue our discussion, our quick review, honestly, of Common Lisp in preparation for our ongoing series on paradigms of artificial intelligence programming case studies in Common Lisp. The last time we covered basically chapter one for all intents and purposes, but we didn't really cover a couple things that are in chapter two and chapter three that I thought would be interesting to cover today. So, as well as covering some of the examples and exercises that they provided, just to kind of, drive home some of the approaches that Peter Norvig takes in his book. One thing I want to mention before we begin today is for folks who are reading the book and are looking for a lot of the Lisp examples that are in the book. Now, a good portion of them are actually available on Peter Norvig's GitHub repository under the name PAIP-Lisp. Now, we will be covering and kind of going through some of that in that repository in later episodes of this series. But I thought I'd mention it here, and I'm going to post the actual link in the YouTube description for our viewers on YouTube for future reference. And for those of you who are on the Jitsi channel, if you guys would like to jump ahead, it's just basically github.com/Norvig slash PAIP dash Lisp. But, you know, I thought I'd mention it here ahead of time before we kind of begin, just because there was going to be a lot of stuff that we're going to be covering in there later on. Last time we kind of covered, like as you can see in my buffer, a lot of basic stuff inside Common Lisp as we've kind of gone through some kind of things that I've forgotten just because of the fact that a lot of libraries ended up taking somewhat of a different approach than vanilla Common Lisp took in terms of designing APIs and such, that I thought I'd go and review because a lot of the examples that are inside paradigms of artificial intelligence programming follow kind of vanilla Common Lisp. Okay, he tried to actually go out of his way to not introduce any external libraries because, again, at that time when the book was published, Common Lisp wasn't actually standardized. So any notion, and even further, I think this is something I should have mentioned last time, but I'll mention now. The notion of packages may have existed, but the notion of systems did not exist. And this is something that is very important to understand for folks coming into Common Lisp. Def system was only available in a lot of commercial Lisps, but open source Lisps didn't have this notion of being able to take a package and being able to load it into the system in a clean, portable way. It wasn't actually until I believe it was the late 90s, early 2000s, just around the time that Practical Common Lisp was published, that ASDIF, another system definition utility, became kind of the de facto standard amongst the Lisps to actually load in uh, packages and libraries into multiple Lisps in a portable fashion. So thank I'd like to thank actually the folks who created that utility, that open source utility, very much so, because I think in a sense it was that introduction of ASDIF and its ecosystem and subsequently successive tools such as QuickLisp, Quick Project, Quick Docs, and so forth, that really allowed us to kind of go into this bit of this Lisp renaissance in a real uh, meaningful fashion, whereas before it was done in somewhat of grassroots fashions. It was a little bit more systematic nowadays. Um, I thought I'd begin with today's discussion with just a couple of exercises that the end of the chapter one brought up that will kind of introduce some of the examples that we're going to be covering today, just for from the vanilla Lisp standpoint. One of which was just basically uh, the notion of tracing, as well as there's some exercises in the book related to like computing dot product that I thought would be interesting to cover, just because it introduces some stuff that people forget about when they're using the examples on a lot of folks' repositories, but don't necessarily use on a day-to-day basis with some of the Lisp APIs. So I thought I'd begin with that. As usual, this is kind of a free-for-all discussion. So for folks who are um, having additional questions around Common Lisp and its development utilities as we go through these examples, by all means, post your questions on the live chat in the live stream, and or for folks who are on the Jitsi channel, go ahead and post your questions on the Jitsi chat, and I will address them as I see them. Um, so the first thing that I thought we would cover is again the exercises that were at the end of chapter one. One of which was essentially compute power for which is the exponential for a given base and power. And another one is actually given excuse me given a a list of atoms, can we compute first the length, the number of atoms in a list? And this is somewhat interesting because of the fact that it's talking about more like leaf nodes inside of a tree, and the other one was essentially count the number of atoms in a collection that is passed in. So basically, if you have a nested structure, um, sorry, number of instances of a particular atom in a collection that is passed in. And one reason I'm kind of writing it out for this is while I'm kind of covering some of the examples live, if you get folks have their Lisp buffers open, you could you know more or less jump ahead and post your answers, and we can have discussions about some of those suggestions that you may have. And finally, dot product. And dot product I think is particularly interesting just because the it reminded me of something about MapCar that I know for folks who use MapCar on a daily basis probably are aware. But I other than the one that you see in line 30, the usage on line 30, I don't use it very much on successive lists, which shows you a nice little trick, and actually makes things a little bit more cleaner. Throughout this, I am going to jump in and out of the different chapters, mainly because while chapter two was more of, hey, let's learn how to write and understand the power of Lisp by writing a basic AI program, which is why I want to cover chapter two. Chapter three was actually not an exhaustive, but a good overview of the APIs that Dr. Norvig used throughout his book. And in particular, one must uh, pay attention to his use of struct and def struct because he calls out a lot of his stuff and uses of def struct, and then brings up uh, object-oriented programming through class. But since class wasn't standardized at the time, a lot of the examples that he leveraged ended up using the def struct approach. However, that being said, in his repository and in later examples, he does build up, it looks like, an OO kind of like structure that looks like class inside a common list. So we're going to see some of that too as well. So because of that, as I jump around, I'm going to start introducing some stuff about his definitions of Lisp style. And there's about 6 principles that he brings up that are, I think, pretty useful to actually recognize when we are, writing our Lisp programs. Um, So the first one that we're going to be covering is, exercise is how to compute exponential between the base and a power, right? So this is obviously something that you could do pretty easily. It's going to be most people do it quite naively. They can, take x, y, two arguments, and they can just, naively write, uh, you know, uh, a let statement here that takes in one, and then um, obviously do, oops, sorry, I just realized that I got out of the let form. And then inside of the let form, we do a do times um, I, y times, go ahead and do a setf res times x. This is a somewhat of a linear time algorithm that most people are aware of that you could just whip out pretty quickly. All right, and this would do basically what you expect it to, when you compute um, power 3 2. You can see that it will do exactly what you expect. But for folks who are aware of successive squares, which is basically if it's an odd number, it's just the you can think of if the power is odd, um, that is if y is odd, then we compute the result to being x times y even, which is essentially going to be just x to the y divided by 2 squared. All right, and this will actually give you a logarithmic based calculation um, for power. And obviously, I'm sure many of you have actually, you know, uh, probably written this way. The one thing that I want to bring out is there's two ways of actually technically writing this in Common Lisp. One is obviously you could just use the expt function, which is basically the exponent function. And for folks who have not seen this, expt is the actual power function that takes a base to a power and then computes it. But so I thought instead of using that function in our code, in our own user-defined function, why not just, do what I would do if I had not known about expt, which is if I do power 2 here with xy, I would end up creating an flet on a function called square that just squares a function here. Um, x, 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 and then in here, I'll then use a con to write, kind of the base cases of this. So if we passed in, y 0, obviously we return 1. If it's an even power, like we said earlier, we just do um, square of the power 2 of x y divided by 2, so we can actually get the half of the actual calculation, and um, the default case, which is then going to be the odd case. So then at this point, we just do x times power 2 x 1 minus y. So this is another way of writing this function. So we can now see power 2, 3, 5, computing 243 at the same time. All right, nothing major here. A couple things that you could do with some of these utilities is you could see the trace, if you will, of this. We will actually leverage trace2 later on when we talk about the grammar example because I think it's an important thing that we cover about tracing in that example too as well. But just to show you how this works is trace basically takes in the function that you want to trace, and then if you just call the function, um, you'll end up, you know, going through and then just tracing it down. In this case, obviously, since there's no recursive calls in Power, it won't necessarily do anything special. But if we ended up tracing, say, Power 2, and we do the same here with 3, 3, sorry, not E, we end up seeing that power 3 calls power 2, and then it actually defines how many calls it gets, and then you could see the actual successive computations in there. So this is pretty useful for stuff that, obviously if you're not entirely sure how the intermediate computations are being created, this trace function would be beneficial for you folks. The other thing that we would do is we're going to cover is just using this kind of recursive style, we could then start, quickly writing the two other exercises that he provided. One was defun uh, uh, count atoms, and this takes in a list. And then what we could do is we could do cond again, and we check to see, we have three cases here, right? Because obviously if we're going to write in this recursive style, we have to make sure what the base cases are. The first base case is are we dealing with um, a an empty list, okay? And if we're dealing with an empty list, we're going to just return 0. If we're dealing with an atom, we just return 1. And then obviously for the base case, what we could do is we could just do count atoms uh, uh, the of the car of the list plus atoms of the cdr. Or you could use first and rest. That's what Dr. Norvig uses as well, but I'm used to just doing it this way, so I just end up almost going back to car and cdr. So we could do something like this, and we grab, say, ABC, and we could see that it returns 3. What's nice about this is if we do A, B, C, you'll end up still getting 3 as an atom. The question is now is what are you going to do if you have, say, an empty list like this? What would it do? Rightfully so, this would actually generate, a 2. The the count number of instances of a particular atom is basically an extension of this function here. The only difference is obviously we check to see if it is here we'll have a check to see if it is the same value of the the key that we're actually that we're looking for, and then if that is, we can return 1, but the recursive call can stay the same. So I'm not going to really cover that particular example, but I thought I'd mention it here just so folks are seeing this. And quickly, one might and notice as they are, you know, uh, looking at these examples that I've just shown that there's a lot of use of recursive functions. And that's kind of what a lot of these examples that are in the book are going to be leveraging. Recursive functions are actually heavily used, and it maintains somewhat of a functional style for uh, the examples that Dr. Norberg was providing. This was kind of a standard practice even a long time ago. They would end up creating essentially a recursive function with an accumulator to implement loops for when using tail call recursion, and then a lot of the higher level functions ended up leveraging those tail recursive functions to write out their higher level abstractions. But um, it's important to kind of recognize this as you go on, that at least for the base examples, you can end up almost writing a recursive version of this, and then you could go back and retroactively fit iteration wherever appropriate to, you know, at least be able to have a brute force version and then work your way up into something a little bit more efficient. Which brings us to dot product. Now, when I originally wrote the dot product one, I will not lie, I kind of wrote it very naively using uh, what's it? Um, Using loop, actually, of all things. Um, Obviously, you can use other things. So the dot product version can, once you do UV here, in your arguments here, you can end up doing something like this. First, obviously, the first thing we want to do is check to make sure that the lengths of the two vectors are actually the same. So you assert the test form and make sure length of u and length of v are the same. Okay. Otherwise, you do want to actually spit out saying that they're not the same, so you don't have to compute anything. Um, if you use error, error can also be leveraged in this case when they're not the same. I'm using just an assertion here for simplicity. And here, what we could do is you could then just do for what's it? It would be for I uh, below length u, and then what you could do is you could say summing the dot product of, sorry, the product of ui time, times vi. So here you can see that this, if we just do my simple dot product of 10 and 20 here, and then put 2 and 3, you'll see that it's 20 plus 60, which is 80. Okay. Now, this is again, a nice naive approach to actually implement this. But what's even simpler about this is if you end up using mapcar, this becomes even nicer. And this is something that I've forgotten. So mapcar actually takes successive lists, as people may have seen in um, the actual mini buffer signature when it pops up. And let me just give me 1 second. I'm gonna just show this on in the actual REPL. Uh, but what that means actually is something that I've forgotten. Mapcar doesn't actually successfully call the function on every element in the list. When you pass in multiple lists, you can have a multi-argument function, and it does an element by element calculation for each one of those things. So what this means is if you end up, doing like calling this star on two lists, say 1, 2, 3, 4, you end up calling essentially 1 times 3 plus 2 times you end up getting a list of 1 times 3 and 2 times 4. All right, so you get 3 and 8, which is pretty useful because now you don't have to write all this code all the time. You could just simply just call mapcar to compute the element by element addition for you. So then this then becomes a simple reduction, right? So, we could just call reduce on plus with map car taking star and of u and v. And this essentially gives you the same, sorry, the same calculation that we saw earlier when we called that product. Okay. The difference is now it's a one-liner. Okay, one, two. You're using two library functions. There's no additional code, so you're kind of expecting that the standard library functions would do what they're expected to do. Okay, and for folks who actually understand the actual language, this becomes very very straightforward. They understand the intent. Now, one thing that I do know that the book uses quite a bit that I'm going to mention here is although I'm using reduction here, which takes in a sequence type, originally older versions of Common Lisp, depending upon older versions of Lisp before Common Lisp was standardized, uh, they didn't have reduction as part of the standard API, but they did have apply. So you can actually use apply here, and you could get the um, same result. Okay. So this, if we just simply change from reduce to apply, we end up getting the same thing. Okay, and that's pretty cool. Just give me 1 second here. Um, just checking to see if there are any questions on the stream. Okay, there's a question here. Is there any benefit of using less than to define instead of just squaring the numbers directly? Um, okay, so good question. Is there any benefit of actually calling creating the flat to square than actually squaring the numbers in using expt2. Uh, I would say that you can use the standard function. All right. For the sake of example, I went ahead and actually added the the square example just to kind of illustrate that you can implement the successive squares without pretty easily. Um, EXPT2, if you can use it, if you can use the external exponential function that's in standard Lisp, go for it. Just use it. All right. And in fact, you don't necessarily need to write power because EXPT already is power. So you don't necessarily need to actually leverage it. This is kind of one of the reasons why I ended up picking up the square example than the EXPT example because the book actually covered the exponential example. And I was like, what's the point of actually calling exponential when you're actually implementing exponential, right? So just like it doesn't make much sense to just use the standard. If you're going to do that, you may as well just use the standard library, right? So I decided instead of actually leveraging that, I was like, it's just an implementation of Square. I'll just implement Square. I mean, it's not that big of a deal. One thing you can do here, even in this example, that also is a possibility, although I would not recommend it, is you could have written that square instead of using flat, literally has a let that takes the intermediate return of x and then computing the square directly in there. But I don't know. Honestly, that's a question for the optimizer as to whether or not that would actually generate efficient code or not, because you are assigning it inside of a closure and then computing an intermediate result, whereas here you're creating essentially a function pointer to actually get invoked. So um, that's something that we would probably have to go and disassemble and see kind of the differences are um, between creating a let here that will take the value of the power to the recursive call and then directly doing star x time xx here versus in defining an actual function. Other questions? Okay. All right. So So that's the end of kind of my understandings of like chapter one and the examples here. Again, a lot of stuff that we've kind of covered quite a bit. Um, in chapter two, one thing that they brought up, sorry, that Norvig brought up that I think was interesting to kind of keep track of is the advantages of writing rule-based grammars versus trying to write something from, say, just basic functions. Okay. And the example that he used, and I'm just going to go and put up the rule-based one, but then I will implement the from scratch version too as well, is, hold on, not bigger grammar, not this one, hold on, ch2.lisp, there we go, this one. Okay, so we have an example of a grammar. All right. This is specifically something called a context-free phrase structure grammar, as indicated by the book. And I thought I'd explain what that is for folks who may not have covered natural language processing at some point. So, um, for newcomers who've never touched this kind of stuff before, who have never touched even, implementing something like, say, a BNF for a compiler or anything, the notion of a phrase structure grammar is pretty simple. All right. Um, in a given language, whether it be spoken or not spoken, you have what you would consider to be a set of valid sentences. All right. Those valid sentences consist of valid phrases. Okay. The notion of this actually comes from an area of a sub area of linguistics called Chomsky linguistics that actually informed how computer programming languages are created. Feel free to look that up. But the basic idea is given this known set of valid sentences and being able to actually understand what types of phrases you're creating, you can actually uh, diagrammatically tag specific parts of a sentence and then use that to create a structure, a tree-like structure of a sentence down to its basic uh, indivisible components, which is usually noun, verbs, articles. Later on, we'll introduce things like adjectives, adverbs, prepositional phrases, and so forth, especially if you're talking about spoken languages. In this example, he only uses a pretty basic phrase structure grammar. He doesn't, and additionally, later on, you would recognize that this phrase structure grammar still also allows certain what we would consider silly sentences to be constructed that are actually perfectly valid. But it doesn't actually do any sort of like error checking or semantics checking on the actual meaning of a particular sentence, but it does generate valid sentences, and this is kind of the notion of what the grammar consists of. It's context free because of the fact that it can generate multiple of these sentences. I don't want to get too much into kind of the theoretical parts of it, but feel free to look up what the notion of context free grammars provide you. The one thing I want to show here is this notion of what they call what these rules are, what he uses in terms of symbols versus and how they get constructed. But to start with, you have kind of the most indivisible pieces of the sentence. These are what you are called your terminal symbols. Okay, and when these rules get invoked, they just kind of choose one of the possible values that are available in here. Okay. And from here, we could create what are called non-terminal symbols. Okay. Non-terminal symbols can be thought of as recursive cases. Okay. Um, And using these non-terminal symbols, essentially, when you generate any of the non-terminal symbols, it'll keep on going through the tree recursively until it hits a terminal symbol, and then it will reconstruct behind the scenes the actual final value, which will be one of your non-terminal symbols, whether you call it noun phrase or verb phrase or sentence. So in the first approach, what we could do is we could literally write this. grammar as it is. Okay. For this, we need a couple of functions. Okay. One is we need to be able to pick up a random element from some list. Okay. Um, so let's call this random element. Um, and this is kind of one of the helper functions that Norvig also defines in his book in his what's it the in his book. So this would be basically taking the list, and then we'll say random length list. And this will actually choose, a random element that we need from uh, the list. Okay. Additionally, we're going to create a function called one of that returns kind of the list, okay, of the single choice that we picked. The main reason for this is when you're constructing these data structures, you want to be able to at least be able to take the choices and chain them together in a composable like fashion. So this function basically does precisely that. Um, this actually, you know what? Let's define one more thing before we do that, and that is uh, no, I don't think we need that. Let's just check one thing here. In my notes, I have to make sure that I have this correct. Um, where is it? It was okay. So one of just takes in a set, and then we just return kind of the random element from that set. Okay. Okay. So now let's go ahead and define our uh, our terminal symbols. Okay, the reason why I'm working up to the non-terminal symbols rather than writing it as is because there's one more function that we need to technically implement, but I have not yet implemented. In fact, I don't think I would need to, but we'll see how it works out. Um, so the first thing we'll start from the bottom up. We'll create a verb function that basically returns one of the list of verbs. Um, it took, saw, and liked. Okay. Up. Sorry. Okay, and then we'll go 10 our noun, and this is going to be the same thing. It's going to be um, man, ball, woman, table. And you can see that, all these are no argument functions. So if you call noun right now in your REPL, you'll end up getting some random list. The next thing is going to be article. Now, article is pretty funny because at the time the book was written, the way Norvig wrote article would work. But I'm going to show you something here that's pretty interesting. Article, the way it is written now, if you do one of, okay, you might be thinking that you could just simply write a list of the and a, right? You'll end up getting, hold on, did that actually work? Hold on. Earlier it did not work when I did this. It should not have actually generated that, but we'll see. Interesting. I take that back. It may have been just the way I've written it. Um, what I was going to show you is you might be seeing the syntax for duh being highlighted. Duh is actually a keyword in um, Common Lisp. For folks who have not encountered the before. And what DAW is actually, and you can look this up, is it specifies, as it indicates, um, uh, that the form, if you use the, is going and you pass in an argument to the, you're basically checking that the value that you're returning from the form um, conforms to that particular value type. So if you expect the to be an integer, I mean the form to be an integer, you could use the to be like a consequence of actually making sure that the form returns an integer. So it's kind of like think of it like a declaim, but it's not a declaim. Okay. I wanted to kind of at least show that to some of the newer folks who may not have seen that. But it looks like if you quote it a particular way, it actually appropriately generates it. So like if you accidentally did this actually causes trouble because this looks like a function call, and it's a invalid function call. So if you accidentally wrote it like this, you'll end up getting an error. Okay, and that error is that the form is being called, but it's not getting two arguments. Okay, so we now have our articles, we now have our nouns and verbs. Then what's left is really defining noun phrase, verb phrase, and um, uh, sentence. So let me go ahead and split this window so I can actually keep my grammar here for reference. And then we could write the fun verb phrase. And here, this is nothing more than appending, actually, a verb with a noun. Now, you could just simply call append, okay, um, verb with noun phrase, okay. And you could do this successfully. For folks who are looking, you might be thinking, oh, you can't actually define um, this function because noun phrase isn't actually defined. Well, actually, technically, it will just warn. You'll have a style warning in your function saying that you need to actually define noun phrase. Otherwise, it's going to create an unbounded call. So let's go ahead and define that. And this one is just going to append an article with a noun. Sorry, noun. Okay. Okay. So now we have our compilation successful. We have our noun phrase. We have our verb phrase. Very quickly before we move on, hold on. Go back to my REPL. Um, I wanted to show you what this noun phrase and verb phrase kind of looks like because there is one more thing we need to kind of do to kind of correct some of these stuff. Let me see. Interesting. Does this work? Softball. Okay. So let's see if this actually generated. So this is actually doing something simpler than what I did earlier, but that's fine. Okay. The final function that we end up writing is nothing more than this generation function here, which is pending noun phrase and verb phrase. So when you call this, now you end up getting different different sentences that are being created from this grammar, and it's actually a pretty simple structure, because you can actually specify using trace, and we're just going to quickly add all the things that we want to actually have a trace: uh, article, noun, and verb. And now if we call sentence, you end up seeing, our structure here. What we've done is we've called sentence, which first, generates all the noun phrases. So it called article, and article returned an A, and noun returned a woman. And since noun and woman are both connected, so we appended the two, we get a list called a woman. And then we generated the verb phrase, and it'll construct a verb phrase too as well. So this is kind of nice. But one of the things that we may have noticed, or I don't know if you guys noticed or not, is we've kind of hard coded the grammar, okay, into this set of functions. Okay, this is a good first solution, but it's a very limiting solution. Okay, um, and it boils down to um, what's it? It boils down to essentially that if you wanted to create a more complex grammar from this, okay, let's say that you want to add adjectives into your structure, suddenly you're going to have to start restructuring and figuring out how to generate and add uh, adjectives into this function declaration. And it's not just adjectives. Let's say that your rule says that it could have 0 or more adjectives. Let's say that you want to implement clean star. Okay, clean star, for folks who aren't familiar with this, is basically used in regular expressions to indicate whether you have 0 or more instances. Obviously, there's a successive one that also allows you to do 1 or more instances, but we're not going to talk about, all the variations there. The bottom line is to kind of add it to this structure and this code the way it is written, it would take some effort, which brings us to kind of the second part is what if we took this grammar, okay, and hold on, let me do this. Oh shoot, not that. Let me do that. Go up. Let's take this grammar, okay, and let's say that we wrote this as is, okay. What I mean by as is we literally take the structure of this and create a list like this, okay. Now, uh, folks coming from Common Lisp would probably recognize this. This is basically your standard associative list, right? You have a key here, and you have a set of values. So you could use the ASOC call to actually query this structure. Okay, it's a list of essentially associations, and you could get the appropriate rule associated with this. So you end up getting, so to give you an example of this, is we call sentence on simple grammar, okay, we'll end up getting the sentence rule, okay. So let's go ahead and add this to our REPL and set our grammar to the simple grammar. Now, the reason why we have this additional grammar global variables, because later on we're going to do like we have a second grammar that kind of extends this grammar with some additional rules, and we didn't want to kind of like, mess the two up. You could do a side-by-side comparison for the two grammars to understand what was added or not. From here, to interact with this data structure, all right, because essentially this is a data structure that kind of contains the set of rules that we want to kind of interact with. We need a couple of functions. One is to essentially grab the left-hand side of the rule, which is essentially the name of the non-terminal symbol or the terminal symbol, and we'll call this rule the left-hand side appropriately, like what the book kind of mentioned. The second one is the right-hand side of the rule that Norvig defined like this. okay, which is rest of rest, which is technically okay. I would prefer you use essentially coulder, okay, because that's essentially the same thing. Um, it's why not use coulder if you have the ability to do it's a CDR to CDR, right? Rest just seems kind of, I don't know, two function calls just it seems odd to me. Um, so given rule right hand side and rule left hand side being defined, we could define a function called the set of possibilities for a given category, and these are called your rewrites. Okay. Um, so and all rewrite does is it just grabs the rule and then gets the all the possibilities associated with that rule. Okay, so these are your set of rewrites. Okay, um, we do not need this. I've actually defined this already. Okay. Um, with that, we can actually generate a very simple thing that's even simpler than what we had before. Instead of, you saw the list of all the functions that are created. To create now a generation, okay, you can just write your standard recursive function, okay, that takes in, and actually, let me do one thing here. This here, let me do this. So originally, it was written slightly different, but that's okay. We can go through this example. All right. So, actually, you know what? Let me do that first. Let me clean this up a little bit just for folks here. All right, rewrite. There we go. Phrase. Then we need to go here and set this up. Okay. Sorry. When you hit tab, completion, Emacs doesn't copy the completion of the buffer sometimes. Okay. So this is our basic sentence generation function. Okay. Um, what it does is the base case is it's a phrase that we're just going to treat like a list. Okay. The reason why we're doing this is because every function that we've written so far acts on a list. Okay, so this is a list of single elements. So if you generate sentences, you get a list of sentence. Okay, and then we have the recursive cases. Okay, the recursive cases is basically um, whether or not you're dealing with the list. Okay, and whether or not you're dealing with a set of rewrites. Okay, rewrites is a different list. Okay, so in the base case, what you want to do is you want to actually call generate on every. So this, you could think of this as the first recursive case, list p of phrase is looking at the non-terminal symbols. Okay, and the second recursive case is looking at the set of terminal symbols. Okay, or non-terminal symbols that are actually really a mix of non-terminal and terminal symbols. Okay, if you end up writing this and actually calling this now, what used to take maybe 6 or 7 functions, now we have the ability of just simply calling once. Okay, and we now generate all sorts of things. We can also just only generate one aspect of it. If we want to just generate a noun, we could certainly do this. Okay, or a noun phrase, and it's the same exact function. Now, some cleanup here was done earlier that I kind of showed you before, but I'll explain why it was necessary. As you can cleanly see here in 65, line 65, rewrites phrase is actually computed technically twice. Okay, in the condition rule as well as in the generation rule. You can avoid that by just creating a let form. This is one way of actually handling it, and this is something that I did earlier. Um, and this effectively does the same thing. So if you end up calling noun phrase, you still see the ball. If you see noun, you see man. If you call sentence, you'll see a completed sentence. Okay, but notice that all this is doing is now is to write or generate a new sentence, a new rule, a new I mean, sorry, a new phrase or even a list of phrases. Um, it's it's actually it none of the code does acts on the actual data itself, right? Which is something that Norvig tried to get at. A lot of AI programs end up taking this approach, which is what he calls data-driven programming. There are other variations of what people call data-driven programming nowadays, but please put that into context. His notion is you are defining a data structure that naturally documents the way the actual problem that you're trying to actually solve uh, amends to. So folks who read your code understand the intent in which you are trying to actually construct this. And in this case, the grammar is pretty straightforward. Anybody can actually look at this grammar and understand this. And what's nice thing about this is you can easily extend um, just the basic rules as is, and you don't actually have to change anything from the code level. You'll end up getting still a lot of um, I sent if I actually let me call noun. Uh, Wait a second. This is no, no, this should work. Let me see something here. It's not finding my additional thing, but it's also might be the problem is ah when I assigned this, I forgot to actually create. When I did this, I have to also update this guy. Okay, now this should have that. Okay, and now I can actually generate this. Okay, cat saw man, table hit the table, and as you see here, when we're calling generate, it's creating some silly output, and this is something that he brought up. But note notice that the only thing I had to really update is really the data values. None of the code actually for the transformation has been touched. Okay, just the data had to be updated. Additionally, we can expand this to a bigger grammar and add new rules, right? And this is something that I've done in this. Nope. Hold on. Hold on. ch2 bigger grammar. Okay. In this example, we have an extension that uh, Norvig wrote that essentially adds to the grammar that we've already provided, the phrase structure grammar, with additional rules for actually defining um, things related to descriptive sentences, somewhat descriptive sentences. Again, though, for folks who are watching this thinking that this is probably a very simpler solution than what other folks are doing, there's a lot of stuff here that is not included. There aren't filters for dealing with nonsensical sentences, and that the sentences that make from the phrase structure point of view are correct, but from the actual semantics voting view, meaning do they make sense, they're not correct. um, but we're going to ignore that for now. I'm just going to give you this one. Let's go ahead and set this here, and now if we call generate, because we've already defined generate earlier, you could see that it will end up creating correct sentences that don't probably make sense. And I'll let you guys play around with that because it's a pretty neat exercise to see how close it is. and how accurate the like from a correctness standpoint, are they actually correct sentences? It's always a fun exercise to try out. Let's see, questions. Okay, nothing from the stream earlier, and that's from the things. Um, One of the nice advantages of this approach also is it allows you to also write tools against your data structure pretty easily. So in this example here, we could like attach, say, a function or define a function that actually allows us to generate a a tagged structure of a generated sentence. And what I mean by tagged structure um, is it provides you not only the sentence, but on top of it, it attaches metadata to saying, oh, you called this rule and this rule called this. To show you this idea is, let me go ahead and define this guy. And let's generate a tree on a sentence. Okay. This is one example that you could see here working. So we have a sentence that calls a noun phrase, which consists of an article, but no adjective, um, a noun, no prepositional phrase, and then in the verb phrase it recognized that you got a no descriptive uh, prepositional phrase verb phrase that basically said, okay, I have a saw and then I saw a woman, but there's no description of the woman. So the way you would read this is from a sentence standpoint is the table saw a woman. Okay. Um, is that a sense something that makes sense? Probably not, but it's a correct sentence from the standpoint of our phrase structure grammar. Um, Now we could play around with a lot of these examples, but the take-home message I hope you can understand is these rule structures, this notion of defining the problem into a way that could be easily parsed or written in an interpretive way is kind of the essence of a lot of the approaches that Norvig takes in some of the case studies in this book. And I'm hoping we can expand on it to additionally to take on some of the more modern challenges for programming, which include, transformer architectures, machine learning, and so forth. Um, the final things that I wanted to touch base on is related to actually just, some interesting functions that was brought up inside chapter 3 that I think would be useful for folks. And then, the goal is as we go on with our journey, any additional things that could be brought up is would be useful. The one thing I want to bring up importantly before we begin, I start bombarding you folks with a bunch of functions that we may have covered at some point in time, um, is something that Norvig brought up for Lisp style. And this is something that if you go through different code bases, a lot of people have adopted over the years, but often more often than not, new Lisp programmers don't necessarily pick it up until much later. The first thing is so I'm just going to go ahead and write this up in a Scratch buffer. Give me a second here. Um, do I have my Scratch buffer open? Slide Scratch. Oops. Okay. Oh, we've already covered all this. Um, okay. So the first thing I wanted to bring up is something that he brought up, which is hold on, sorry. being specific in your code. Okay, and well, let me just go ahead and write out all six things. So the first thing that he said is be specific in your code, use abstractions where appropriate. Okay, um, the be concise, be as concise as possible. This is something that is often overlooked. Okay, um, use the appropriate tools. Okay, well, provided tools is what he calls it. It's the same. It's kind of the same thing though. The provided tools is use the language to its fullest extent where appropriate. Um, don't be obscure and be consistent. Okay, and we're gonna go through each one of these one at a time. Okay, the notion of the first three should be obvious to any intermediate level programmer. All right, being specific, using abstractions, and being concise. Okay, a lot of that is also related to intent of code. Some of the examples that you saw earlier, you saw the way I wrote it. Technically, for most people, the newcomers, everybody would understand the lowest common denominator in the example that I wrote for power using loop, for example. Okay, um, is that algorithmically efficient? No, I mean you saw the successive squares is a clearly much faster uh, terms algorithm in terms of complexity. Um, but for most folks, they would think that the loop version or even the do times version is more concise and more specific because of the fact that they're more familiar with it. So there's a trade-off and a balancing act to understand where that kind of fits. Okay. Um, the concision also is important because there's less of a chance for you to make mistakes from the point of view of correctness. Because if you especially use point number four, the provided tools and the APIs that are provided to you inside Common Lisp for writing these kind of declarative types computations, your code will naturally become concise just because of the nature of those APIs. I'm not saying everything is perfect, okay? Again, I'm going to reiterate what I said last week, which is, and I've been saying throughout our journey on this stream, Common Lisp isn't a perfect language, all right? There isn't a such thing as a perfect programming language, but it is I would say, a compromise and a well done compromise of all the active lists that were done at the time and the additional libraries that were provided later on really brought up a style that's more functional and syntax driven in terms of creating DSLs than other places. So being able to provide that API that naturally fits a particular problem domain is probably the ultimate goal of any good software design. And this is something that Norvik kind of drives home with a lot of the stuff that he brings up here in terms of the six principles for Lisp style. Um, one of the examples that um, he brought up is creating for any data structure, creating functions to get components of that data structure. Just so rather than saying, "Oh, everybody should know that," what I said earlier, which is that CDDR um, is the rest of a list. Um, it would be useful for us to put a name associated to what the intent was of what you were trying to grab inside in a data structure that you decided that was supposed to be a tuple of different values. Okay, and this way your code will be much more cleaner and much more maintainable.
So, Rom,
Yes.
uh, I think this came up years ago when we were talking with actually Shay. Um, it's basically a lens, right? Haskell would call that a lens, which is
Define lens now. I
okay. You asked me that years ago, and it's basically I gave you. It's like cadaver, right? So it is a well-defined way, a predefined way to go into some data structure and pick out exactly some sub data structure, whether it's an atom or another structure.
So I know
Uh,
I've asked you this question. Other folks on the stream may not have known this. So
okay,
so
so
try to elaborate on that a little bit.
okay, sure. So there, I think you can go up to like 9 A's and D's,
Yeah, something like
and
that.
yeah, so you can go data or whatever, but that doesn't make any sense. At least it's not intuitively obviously what you're trying to do. So then you attach a function name to it, and then you can say like call last name on this record, right? And then you can get back the last name, something like that. So, but it doesn't have to be return doesn't have to be just an atom. It can be an entire data structure, right? So you might have some really huge data structure, and you can go like, give me the weather patterns on Earth, right? And that can come back. So
Right.
I think, as I understand it, I'm not the Haskeller. You can talk to someone later today. Um, but I think lenses are basically a way of having a well-defined, shorthandable, short nameable way to get into a data structure. So Haskell, since its data structures are, you know, the, any list has to be, all items in a list must be of the same type
Right.
in Haskell,
Right.
right? So
Right.
well, that takes out a lot of. It's like you must be this high to attack the city, right? You must be this tall to attack Manhattan or something like that. You've taken the if it is a list of this type, then you've taken out a lot of. It's very similar to. Well, anyway, never mind.
So this is kind of why I was bringing up this sort of stuff with the list style because again, since we are talking about a field now, we're talking about artificial intelligence programming and the notion of defining algorithms and programs that are providing some form of what people are calling intelligence. And I'm saying it that way because folks who know me and who have heard me on this channel or in other discussions know that I have some opinions on intelligence and the search for artificial intelligence. But I'm not going to get into that because um, it's a very interesting topic. It's a whole series of podcasts that I could probably create at some point, but I'm not going to do that today. Um, but it's important to note when you're designing these systems that, or any large scale software system, that the intent of the code must be as specific and as precise as possible. And I think at this point, the reason why Norvig brought this up, instead of in the first two chapters, is because the goal is now, okay, we're about to embark on a pretty large scale topic, designing systems and programs. You want to be able to write these so that 6 months down the line, if you ever revisit them, you'll be able to understand what the hell you wrote. So it's an important piece that I thought we should at least kind of reiterate today. So some examples of this that are already in the standard library, because I've heard people ask questions about this in past discussions about Common Lisp, um, is the when and unless forms. All right. If folks who have never seen when and unless, this is important to kind of understand, try to really drive this home. When so normally every programming language has the if statement, right? And if takes two arguments, right? You have a essentially a condition, you have a true branch and an else branch. And any known person who's written code has done something like I don't hold on, where they know that the value is going to be um true, all right? So like two is less, uh, three is less than four, and they only write uh, something like this, okay, but never add the optional else statement. Okay, even though folks who know that you are writing that there's an implicit else there. Okay, um, naturally, there's no else in this case because of the fact that I've given constant values. But you could think of some condition here. If you're writing code like this, where you know that either the the true branch or the false branch is always going to end up happening, then leveraging instead of if um, the appropriate when or unless um, would be uh, very useful. You know, um, and so that's something to be aware of. So unless is also the opposite of this here, right? So this is something to at least bring more nuance to your code and allows your code's intent to be more well documented. And there are other utilities like that around, um, especially when you start getting into the notions of creating, which is a pretty standard pattern, design pattern, but I wish more people would use it, is the interpreter pattern. If you use it for other languages that don't necessarily have the facilities of doing syntactic abstraction like Common Lisp does, um, there are advantages of having that kind of domain-specific language embedded into your language. Okay. A couple things that I want to bring up along these lines, one of which is something that I'm sure most people have seen at some point but forgotten, is the case statement. So you have case, type case, and then they're appropriate of E type case and C type case and C case. All right, what are these differences? Um, Case is pretty obvious. If you see case here, and I'll just write it in the buffer, in the Lisp REPL. If we do case, well, let's first define a parameter x and say 5. Okay. What case allows you to do is you could simply write now cases like it says here, has a name indicates, and it will take that constant and just do a match against constants. Okay, this is different than a switch, which is cond, because it's not conditional. It's generating the condition in almost all cases, right? So you could write these things like this, and then it will end up shooting out a nil. And if you end up using E case or C case, in one case, let's say you use E case, you'll end up getting an error because the value passed in doesn't match any of the conditions. All right. Because and since it fell through, you'll get an error. If you use C case though, um, it's a continual error, which is for it. If you want to write a continuation, it's basically a condition that allows you to change it to something that matches one of the values. So we could supply a new value now for x here, and say 1, and we could see that here that 1 has occurred. And if we do x here, you see that x has also been appropriately updated. All right. So type cases is for type driven things. If you're using a type case, it's essentially creating a cond that calls on type P to make sure that the type that's being passed in is of a particular type. You don't need to write all that code. Type case will do that for you. You can use type case to implement some of the things that you'd seen in languages like, say, Haskell, like Disp. I think it's the show type class and things like that. You could definitely implement using typecase, but you would have to implement it yourself rather than the language will generate some of that for you. Um, we've talked about generalized expanders quite a bit. I don't think I'm going to actually really touch base on that. One thing I will say is Norvig does make a suggestion that if you are using generalized expanders, which is basically setf, um, well, first, there are built-in functions that essentially does some of the same stuff that setf does. Like for example, many of you may have seen this function, replica, I think is replace car. So if you end up doing something like this and you do 1, 2, and then pass 3, you end up seeing that the car, as it says, it will replace the car with the first value with 3. So this is basically the same as set of list 1, 2. Sorry if I did first here of that. It'll be this. It'll do the same thing, but oh yeah, sorry. I have to actually first define a variable that actually does this because it doesn't do this on the fly like replica does. Let me do quick LST list 1, 2. Okay, and let me just say that LST. Oh, sorry, car LST 3, and then return that. And you can see that it ends up doing the same thing. The same thing actually occurs with uh, the coder version of this, which is okay. But the difference is you may have noticed that the car would return an actual list, but the coder is actually a dotted pair. Um, in order to do replica coder, you have to actually um, rip out and create a new cons pair there. So that's kind of the difference there that you need to be aware of. In general, for I think consistency, a lot of the examples that we're going to see in the book do not touch these APIs, but it is something to be aware of when you are looking at older code, um, especially some of the code that's written in some of the examples that he provided in his GitHub repository. I believe he uses some of this stuff. The other thing that he brings up that I don't know about if this is still true today, I wish I could get some opinions on, is the use of set Q versus set F in generally. Um, so a lot of books that I've read in what we would consider the modern Lisp Renaissance age, that was appropriately considering using um, set F always, but in PAIP, Norvig says if you only want to set a variable, the special form set Q can be used instead. I don't know why he would suggest set Q versus set F, and I'm guessing maybe it's because of in the set F case it has to look up um, the object expander that's available for that type, and if it's not specialized, it will throw up an error. But set Q, if you're just dealing with a simple cons value, you could certainly just use set Q um, for the same thing. So like if I wanted to do star x5, this will have the same um, uh, behavioral result as doing um, set F. Both of these essentially do the same thing. They'll modify the value. Um, but others who are on our stream, if you know if set Q is still useful today, please let me know. Post it in the comments, and I will, um, mention it to people next time. One final thing that I thought that I would also bring up, and again, chapter 3 is really just a review of the language. So folks who haven't actually really done a lot of stuff with Common Lisp, if you want a quick review before we actually jump into AI case studies, feel free to leverage this. Is the number of so it's pretty funny. Um, the chapter, I think other folks should see this themselves. The chapter actually goes through and implements length 14 different times, um, some of which I didn't even realize what that some of which I was like, huh, why would you even write it this way? Uh, like one of the examples that they gave is using do list and then incrementing a counter variable rather than just using, say, loop to actually do this. One of those implementations leverages loop. Um, you can go through that too as well. It's pretty interesting. I would encourage those folks who haven't really played around with this to really um, look at that chapter in those implementations to get through that. Um, is there anything else I want to touch base on? No, this is all stuff that we can cover as part of. I think that's all I have for today. Um, I am just looking at my notes here, and in the meantime, the last 20 minutes, I'm opening the floor for questions and discussions, really. Anybody who has a thought about how we are about to embark on this, let me know. Otherwise, next week we're going to actually start on our first case study, which I'm excited about. This is chapter 4 in the book on uh, what is it? What's it called? I think it's the GPS one, the general problem
Yeah,
solver one.
general problem solver.
Yeah, it's general problem solver. Yeah, yeah, I'm excited about this one because it's going to be pretty interesting. Um, we will go through some of these. We're going to be playing more with the exercises as we go through some of these things. So, folks, I would encourage you as we are, um, what's it, as we are traveling down this path to kind of read some of the material up front, just because this way we could discuss um, the um, the exercises, and we could try and play through the exercises together on this stream and discuss some of the confusing parts of this chapter as we go through it. Um, it is a fairly long chapter, so this might take us. The description itself might take us some time to at least understand, and then um, go through how we would implement some of these stuff using some more modern practices for like writing tests and things like this, because section 4 actually talks about testing the program with some general inputs and things, and I think that would be useful to actually go through as we are um, going through that chapter the first time. So, are there any other questions?
No, I'm good. Thank you. Very interesting.
Thank you guys for sticking around through this fire hose of information, but I do appreciate all of you out there who have been following us. Like or subscribe to our YouTube channel. Folks who are on the Jitsi channel, please uh, make sure that you uh, stay up to date with our meetup to get new talks and updates regarding both Common Lisp and other languages that we may be encountering too. As usual, I don't think I have to remind all of us in the FP world. AFP is looking. Um, oh, there is one question that just popped up. General question: do you recommend? Okay, so someone asked about, do I recommend PAIP to learn Lisp instead of Practical Common Lisp? To learn the language, um, I would say Practical Common Lisp is probably what you would consider your traditional languages learn programming language book. It's an introductory book. Um, there are plenty of other ones that I've written out there like that. Um, I would say PAIP is for folks who have enough Lisp knowledge to quickly go through chapters 1 through 3, and then learn Lisp style, because a lot of stuff that we consider to be modern Common Lisp does trace, at least in some way, shape, or fashion back to PAIP. Um, and some of its techniques are heavily used. People take it for granted today. So I would say Lisp style to learn programming, like software engineering in Common Lisp. This book is actually a very good book to keep it on your shelf, along with actually Guy Steele's Common Lisp, the second edition. Common Lisp Language Second Edition, because that's kind of the definitive source of Common Lisp outside of the ANSI standard documented source. That's on top of also the XML. Um, but in terms of actually learning the language, you're not going to learn everything, all 800 functions, and how to use a lot of those functions uh, cleanly in PAIP, just because, again, it was written right around the time that the second edition was being published and the standard wasn't complete. So stuff where you would want to use object-oriented programming doesn't in a depth class doesn't come into play because it creates an old like dialect in there as a case study. So, other questions? Great. I will
Where,
see you guys next week. I appreciate you guys staying on this Saturday. And have a great evening, morning, afternoon, whatever time you guys have. And I will hopefully will enjoy this book together. See you guys later. Bye.
thank you. Where are some of these questions coming in from? I've only connected through the Jitsi, so should I